Okay, today we're going to start our last topic in calculus, and that is finding volume. I know, it feels like you're back in geometry class. So I need you to consider with me, if I was able to do this with you in person, the first question that I would ask you is, I would actually probably put one of these in front of you. I'm trying to, my pictures aren't the best, but I've tried to give you two different fruits that we have. On the left is a lime. That's what that's supposed to be. And on the right is a lemon. And if I were to give you either one of those, how would you find the volume? Give me the most specific answer possible. Now, obviously, you don't have it in front of you to measure things. So I just want you to think about process here. What would your process be for finding the volume of those two real-life objects that we never talked about in geometry class? Why? Because they're not perfect spheres or cylinders or cones. We have these lovely formulas in geometry, but what about all the things that don't fit a formula? What about all the non-perfect, irregular, whatever you want to call it, objects that we have? So I need you to engage with that question for a minute. The more you struggle with this question, the more profound the results of today is going to be. Okay, I hope you had a little bit of fun. Maybe you got a little frustrated trying to figure out, like, what am I supposed to do? And there's not really one right answer, but I want to talk about what would be kind of more specific and more exact in terms of our answer. I'm guessing that many of you kind of chopped it up in a variety of ways. For instance, one thing that I see is sometimes people will try to kind of chop the ends off, and then we have a cylindrical middle. Find the volume of that cylinder, and then maybe we can put these two ends together and make a sphere. Kind of, not perfect, but we could do something with those. So same kind of thing would kind of work here. Not a perfect cylinder in the middle, but we're going for approximate. So that's not a bad idea. Did anybody do anything else? Yeah, I know. I'd love to hear your answers. So I will definitely read what you guys put in the comments for your question that I just asked. But let's talk about a different way of doing this. And maybe I should expand the question. What if that was not just a lime or a lemon? What if it was something else? I don't know if you've ever seen those party decorations that are roundish. They start as a flat thing, and then there's like paper in between the two cardboard pieces that when you pull it out and put the two cardboard pieces together, then it makes a... So it starts like this. I just found some that my grandma had, and I think they were bells, maybe from a bridal shower or something. So it starts like that. It looks flat. And then what happens as we pull this out and pull that around, it actually makes a three-dimensional thing. So the two pieces can meet, and then you've got this like expanding paper, I don't know how to describe it, that will make that a three-dimensional thing. So what if we have something like that? Okay, now we're getting very far away from a sphere, right? I don't know that we can find a cylinder and a sphere here. So what I really want, as is always my case in calculus, is I want to be able to deal with everything that falls outside of the bounds of straight geometry. So how can I use geometry to help me? That is the question. Well, cool thing about calculus is I have a tool that allows me to add up a whole bunch of things. Yep, remember our integral? Integral is a summation tool, and we've used this to find the area of a two-dimensional figure by adding up a whole bunch of rectangles. How can I use that in the three-dimensional sense? Well, instead of thinking of it as a rectangle, what I'm going to think of it as is I'm going to think of this lemon. If I were to take a slice, so I'm going to picture actually just taking a very small slice of lemon out here. Or we could obviously do the same thing with our lime. Or we could do the same thing here. I know this is kind of hard to draw, and you don't actually need to take notes on this yet. This is just kind of my introduction. For any of those, no matter where I slice them, now picture that slice moving. What's happening is that slice is actually Matt, I need your help here. I'm trying to draw a perfect circle. It's actually a perfect circle. So the thing is that the circle is just changing size. When I get down here, I can still take a slice. It's still going to be a circle. It's just going to be a smaller circle. And that circle is changing. But suppose I had a way of expressing the area of one of those circles, or better yet, volume of one of those circles. I definitely have a radius. So I could do the radius. Area of a circle is pi times radius squared. And then if I gave it a very small height, so we've got this really small width of my slice. And if I gave it that height and make this not just a circle, but I know this isn't a great picture, but a cylinder, a very short, squatty cylinder. So what I'm trying to draw is something like this. Then I could find the volume of one of those cylinders. And then I could add up all of them and end up with my volume of my entire figure. Same thing would work with the bell that I tried to draw on the bottom. So you can kind of picture, okay, I've got this, whoops, that thickness there. And if I did a slice down here, it would still be a circle when I pulled it out. And you may have tried to do that. So I do have, when I do this and actually bring in lemons and lines, I always have students that do try to slice it up and figure out and the idea is if we make the thickness small enough, then the fact that they're not a perfect circle becomes irrelevant. We're making that thickness essentially go to 0. That's what an integral does. That thickness is going to be my dx or my dy. So we're going to jump into a problem, but I want you to kind of keep that visual with you. So this is actually not section 8.3. Let's fix that. That is section 6.3, volume of 3D solids. And today's objective is going to be to find the volume of what we call a solid of revolution. Formed by revolving a curve about a line, which we will call our axis of rotation. So we'll start with x and y axes as our axes of rotation, but that line could be anything, and we'll eventually take it there. So the first question I have is find the volume of the solid formed by revolving the line y equals 3 around the x-axis from x equals 1 to x equals 5. So yes, I do want you to sketch this. You don't have to be great pictures, but I think it's important that we visualize what's happening here. So y equals 3, I'll draw it with you. So there's my line y equals 3, and I'm going to go from x equals 1 to x equals 5. So I'm just going to be looking at the part from 1 to 5. And I want to revolve that around the x-axis. So what happens is that line is coming up and around, kind of like that bell that I was talking about before, those party decorations. And I think it's easiest to visualize this by starting with the reflection. So the reflection of that is going to be right here when I take this piece and revolve it around. And then what's going to happen is that's going to go all the way around, including coming out and then going back behind the graph, if you will. And we're going to end up with a cylinder is what we should be visualizing here. And you're thinking, I don't need calculus for that. You're absolutely right. So I often do this, and I'm going to do this here because I want you to see that the calculus is going to give us the same answer. Then, of course, we'll take the calculus to problems that geometry can't help us solve. So the geometry, you absolutely have a formula from geometry for this, so let's do it. We've used this one before, so hopefully you're remembering that. Pi r squared times height. So my radius, this is on its side, so my radius is 3. And then my height is the distance between the two bases is what I like to tell students. So the height is 4 because I was at 1 and 5. And then let's go ahead and just get an answer here. So pi times 3 squared times 4 is 9 times 4 is 36. I'm getting 36 pi. I didn't give you specific units here, so cubic units. Okay, so geometry got me an answer there. Now, what I want to pose to you is how could we do this using the method that I just kind of outlined in sort of a theoretical way, by taking a whole bunch of slices of this cylinder. So I'm going to generalize this as my volume is going to be, by calculus method, the integral of pi r squared times dx. So this is my circle here. My area of my circle. The dx is the thickness of the slice, which I don't need to specify because that's just a really, really, really small thickness, and my integral is going to take care of adding them all up. So this one's going to look a little bit very much like the others. If we want to kind of picture that, I will draw a slice in here. So a slice that we have could be, just go to some random spot, and here's my slice that I'm taking out there. And when I pull that slice out, voila, it's a perfect circle. I know, Matt, that's so disappointing. Hopefully you drew a better circle on your paper. And I'm trying to figure out what the radius is of that slice. And the radius is not always going to be the same. So the radius is actually determined by the distance from the axis of rotation up to the curve. If that curve were changing, then I would have to use a function there. A lot of times that's going to be whatever your y equals is going to be your radius. And we'll see that. This one is always a constant because it's always 3. So my radius becomes 3 squared. If you want to pull the pi out, we don't really need that in there. And I'm integrating from 1 to 5. That's my x values that I'm going along. And let's try it and see what happens. Okay, so if you want to rewrite that or think of that as pi times integral from 1 to 5 of 9 dx, that's probably a cool idea. Okay, so now I'm doing antiderivative of 9 is 9x, evaluating that from 1 to 5. Or you might be remembering that we have a property that says I can do 9 times, oh, sorry about that, times 5 minus 1. We'll get the same answer here either way. 9 times 5 minus 9 times 1 is 45 minus 9. Oh my goodness, there it is, 36 pi cubic units. And if you're looking at that and comparing the two, totally fair. If you say, well, that was a lot more work. Yep, it was. And that's why we have formulas in geometry for our basic, perfect three-dimensional solids. Let's do one more, and I'm going to do it both ways. So this is going to be another perfect solid. And then I promise we'll get to something that we can't use geometry for. So I'm now going to do the volume of a solid formed by revolving the line y equals 1/2 x around the x-axis from x equals 0 to x equals 6. Yep, you got it. Start with a picture. So there's my line. Like I said, I like to start with a reflection. So take that, and the reflection is going to take me down here. And then if I'm revolving it, I end up with a cone on its side. So the geometry. Okay, you might forget this. I'm not making this up. You can look up the volume of a cone formula, 1/3 pi r squared times height. Radius, so for the cone formula, you do the radius of the base. So the radius is 3 again. That's boring. And the height of the cone is right down the middle. We have what's called the slant height and the regular height. We want the regular height. from the tip all the way to the base, perpendicular to the base. So that's 6. And if we go ahead and get a calculation here, got 9 times 6 is 54 divided by 3. I'm getting 18 pi. Units cubed for my answer. And now let's see if we can get the same answer using calculus. So again, I'm going to do the integral of the area times dx. So pi r squared times dx. And we can pull that pi out. And here's where our radius is changing. And the last one we had a radius that was always the same. Radius is 3 there, but the radius is actually 2 here, and the radius is 1 here. And anywhere in between there, if we take a slice, our radius is going to be different. So what we want to do is picture at some random point. And I actually go for like not a perfect value here to kind of visualize this. So if this is my slice that I'm pulling out, I pull that out, and there's my... I haven't done circles yet in geometry, so my circle drawing game is a little off here, guys. Sorry. There's my perfect circle. I want to express the area of that circle, but the question is, well, what is that radius at random point in time? So it's going to be dependent on where I am on my x-axis. And what's going to happen is it's always from the distance from the x-axis up to my curve. So that's where I use my function. It is the y value of that point right here. And this point is some x comma y equals 1/2 x is how I could express that point. That becomes my radius. So my radius is going to be 1/2 x quantity squared dx. Okay, stare at that for a minute if you need to. We need to put our limits of integration in here. We're going from 0 to 6, and then have fun with the calculus. So I'm squaring first, always simplifying the inside of my integral as much as I possibly can. And then, why not? Let's pull that out. I don't need that 1/4 inside of there. So 1/4 pi, or pi over 4, integral from 0 to 6 of x squared dx. I'm ready to find the antiderivative now. So that becomes x cubed over 3, evaluated from 0 to 6. Fundamental theorem of calculus, plugging in my antiderivative. You could multiply the pi over 4 as you go, or keep it out front using parentheses. 0 cubed is 0, so I have on the left side 6 cubed divided by 3. Holy smokes, I think that's 216 for 6 cubed. Over 12, 216 divided by 12, you can check me. But I am absolutely getting 18 pi cubic units. So I'm hoping that I have convinced you that we have a valid method here at this point, because we are about to enter the world of geometry fails, and I got to use some calculus. So just to give us kind of a conclusion here, you could absolutely write down that if it's a perfect geometric solid, you would not use calculus. But as kind of a method, we've established that the volume is the integral of pi r squared times dx, with my radius being sometimes my function. Usually that's not just going to be a number. And really what we're doing is area times dx, area of my circle. So we could write that as pi times f of x squared dx, where my radius becomes my f of x. So those are some different ways of expressing this. We call this finding the volume, because there are other ways to find the volume, by disk or washer method are the two terms that are used for this. So disk, I guess we really haven't gotten to the washer. A washer is something where you have a, if you've done any kind of building, where you have a hole in the middle, and a disk is just a circular disk. So this can turn into washer method, and I guess I'm getting a bit ahead of myself. So hold that thought, and let's focus on discs for today. Okay, so more fun. We're going to do a few more examples. Like I said, I want you to see what happens if we have a curve that is not a perfect cylinder or cone. Because basically, I guess there's one other one we could have, a perfect sphere. Otherwise, we're going to end up with other things. So find the volume of the solid formed by revolving the curve y equals radical x around the x-axis from x equals 1 to x equals 4. So we're going to have some fun with this one. This is going to look very familiar to you. So radical x looks something like this. And if you're doing a reflection here, I'm just doing a sketch. Oh my gosh, there it is, guys. Half of our lemon that we started with, right? It looks pretty much like a lemon or a lime. So x equals 1 to x equals 4. Okay, we're chopping off the end of the lemon. Don't want the end of the lemon. So we're chopping it off here, and we're going to end up with this beautiful kind of section of a lemon here, or whatever you want to think. So we don't actually need this part. That is the three-dimensional solid that we're about to find the volume of. And guess what, folks? Geometry fails us here. There is no way to do this with geometry. So enter calculus. So I've kind of established a system for myself of volume is the integral of the area of one circle, multiplying that by dx. In this case, I'm going from 1 to 4. If you want to pull that pi out front, I like to do that. And now I need to figure out how to express the radius. So again, you don't have to draw this every time. Just trying to help you visualize here that this is like my slice. I know these are very hard pictures to draw. So that is my slice that comes out as a circle. So I'm looking straight at the top of it. Obviously there's a little thickness, but that thickness is my dx, so I don't have to worry about that. I just need to figure out what the radius is. And the radius of that is changing as I take different slices. So kind of picture, okay, what if a slice were here? Radius is smaller there. And radius is always the distance up to my curve. So that is the y value. Again, we could picture that point as x comma radical x, and that is the y value is the height there. So radical x becomes my radius. And now I'm ready to do the calculus. Integral from 1 to 4 of, oh, I can rewrite that as just x. What a nice integral. And that's putting me at pi times 4 squared minus 1 squared. That's 16 minus 1, or 15 pi units cubed. Oh my goodness, I made a mistake. Sorry guys, I'm not thinking great today. So hopefully you caught my mistake. If not, I'm going to go back and fix it right now. Integral of x is not x squared, it's x squared over 2. Power rule. So I have a pi over 2. Or you can, so I'm just putting that 1/2 with the pi. Or you can do 4 squared over 2 minus 1 squared over 2. And I'm getting 15 pi over 2. That should be my correct answer. Sorry about that. Okay, hopefully other than my dumb integral mistake, that made sense. And if you're thinking, how can this get harder? Well, I kind of mentioned at the beginning that we're talking about revolving a two-dimensional curve around an axis of revolution. And so far, we've just looked at the x-axis. So what happens if I revolve? Yeah, let's take the same curve, radical x. X equals 1 to x equals 4, but let's talk about revolving that around the y-axis instead of the x-axis. So I'll put both on the screen here just so we can picture it. We're going to start with that same, ooh, give yourself a little room on the left there. So maybe put your picture a little bit more like this. And let's start with the same curve. It's not going to look very lemony, guys. So there was my curve, and I went from x equals 1 to x equals 4. And I'm revolving it around the the y-axis. So that's going to be like revolving it here rather than revolving it there. So picture spinning that whole picture from right to left or left to right, however you want to think of it. And what we should end up with here is the reflection of that curve goes like this. And then basically, so that would be if I was going from 0 to 4. Because I'm starting at 1, I end up with kind of this open bottom. I don't know, kind of like a funnel. These get hard to describe. But that's my three-dimensional solid. So good news. I can still find circles here. I can absolutely slice this and find circles. The circles are going to be the other direction. So if I take a random spot here and try to picture a slice, that's my circular. I'm slicing horizontally across my y-axis, which does this very interesting thing. Geometry is going to fail here, so I'm going to use this space to draw my circle and help you hopefully picture this. So in a two-dimensional world, that circle looks like this. And my radius is distance from the center out. I'm going to draw it this way. And this time the radius is going to be the x value, not the y value. It's the distance over to this point. So my x value is going to be the radius. My thickness, though, we got to pay attention to something else here. And the thickness of this slice is a small change in y, not in x. So remember, my calculus says find the area of a circular disc and then multiply it by the thickness. And that turns it into volume of a tiny cylinder. And we're adding up all of those. So if my tiny thickness is dy instead of dx, yeah, you know what that means. That means everything in my integral has to be in terms of y, not in x. So I just did this crazy thing of changing this to a dy, not a dx. That means that my limits of integration have to be y values, and that means my radius has to be in terms of y. So let's work it out. So we said that our radius was x, but I can't do x. So what I'm going to have to do is take that y equals radical x and solve for x. So squaring both sides, I get x equals y squared. That's going to be my radius. I still have to square it for the formula. The radius itself is my x, but I'm putting it in terms of y. And you can picture that curve. Radical x is the same as x equals y squared, that sideways parabola. So if you kind of turn your graph on the side, hopefully you can see that y squared is that value. I don't know what that is. That looks like weird. Okay, and then I'm going to keep the dy there. And I almost have this set up. I need to get my limits of integration. My limits of integration are going to be y values, not x values. So these are no good. Let's figure out what those points are. So if x is 1, y is radical x. So this point is 1, 1. So the starting point is still 1. But this point here is 4, 2, because radical 4 is 2. So my y values are from 1 to 2. X values would be 1 to 4. Okay, so again, take a minute, process everything that I just did in terms of setup there, and then have a ball with the calculus. So simplifying for myself, now I'm ready to integrate. I got it right this time, guys, my power rule. Y to the 5th over 5 from 1 to 2. Yeah, I'm going to pull that pi over 5 out front. I really don't need to do it every time with it. Just do it at the end. So 2 to the 5th minus 1 to the 5th. And 2 to the 5th is what? 2 times 2 is 4, times 2 is 8, times 2 is 6, times 2 is 32. So I'm getting 32 minus 1 times pi over 5. And if my math is good, 31 pi over 5 cubic units is what I'm getting there. Cool. It should look very similar to what we did with the area problems, where we flipped it and did with respect to y. Obviously, we're taking this to the third dimension, but same kind of reasoning here. I know we haven't done a ton of those. Okay, let's do one more. I know this video is getting long. So we'll wrap it up with example 5 here. So now would be a great time if you want to pause and try it on your own. Or, of course, you can follow along. I'll take you through this. So I'm trying to give you recognizable curves. This one might not be as recognizable. Probably would help if it wasn't in this form. But some of you may be recognizing that this is a semicircle. If you don't recognize that, you could certainly square both sides. Y squared equals 36 minus x squared plus y squared equals 36. But when we solve, we end up with a positive and negative square root. So this one is just the positive square root, which gives us just this. And when I revolve this around the x-axis, okay, we're back to x-axis. Don't worry, we'll do more y-axis eventually. So when I revolve this, we should be ending up with our perfect sphere. So we do have a formula from geometry. This is one that we're going to be able to do both ways and convince ourselves that our calculus is working for us here. Formula for volume of a sphere is 4/3 pi times radius cubed. Radius is 6. I think I hit... Excuse me. When I multiply that out... Okay, I think I've recovered. Volume comes out to be 288 pi. And then, of course, we could do the calculus version of this, which is... I'm trying to do a dotted line. It doesn't really work great. So there's my thickness there. And if I take that, that's going to be a circle. Radius is changing this time. Picture a slice there versus picturing a slice over here. And my radius at this point is going to be just this much. So radius is determined by the height of my curve. So again, that's some point x comma radical 36 minus x squared. Height being the y value there. I just like to start with that general, and then I kind of fix it up. Pi times integral of r squared. So my radius, again, we said, whoops, was that radical 36 minus x squared. Squaring that, integrating from 0 to 6. And that squaring word is working out pretty nice for us. So it's getting rid of the radical, making our calculus a little bit easier, and let's go for it. So your choice, I'm going to keep the pi out front. And I think I'm going to need a little more room here. Although I guess the 0 is going to cancel out. So 36 times 6 minus 6 cubed over 3. And then minus 0, well, 36 times 0 minus 0 cubed over 3. And that is going to go away because all of that becomes 0. 36 times 6, I'm getting 216 minus, I believe, ooh, I messed this one up. Sorry, guys. Let's fix this real quick. Second mistake. I am not thinking great today. So my integral is not from 0 to 6. Did you see what I did there? If I went from 0 to 6, I would only be getting this semicircle that I'm outlining right now. I'd be getting all of this. I missed the other half of it. So I actually need to go from -6 to 6. That was my original curve that I drew in black there, from -6 to 6. So I'm going to go back and fix that. That's going to be a -6 to 6. And yes, I need to fix that here also. (36 times -6 minus a -6 cubed all over 3. And I'm getting 216 minus 72 minus, be careful with your parentheses here. It's a negative 216 plus, because it's going to be minus a negative 72. That's inside the parentheses. Pi times all of that, so I'll just have pi with my answer at the end. So 216 minus 72 is 144. And minus, this is going to be a negative 144. Giving me that same answer of 288 pi. Sorry about that. Hopefully you caught my mistake before I even caught it myself. Okay, we are going to call that good for today. That's a very good introduction to volume. More coming tomorrow in terms of levels of complication. But great work. Minus